So for a quick overview of indeterminate forms, let's take a look at some of the ones that I've scribbled out here. These two right here, these are quotients. 0 over 0 and infinity over infinity. These are quotients. Make a little note of that. And when we have these quotients, when they show up when we're dealing with these indeterminate forms, we can use L'Hopital's rule. To make a little note for yourself, when you have 0 over 0 or infinity over infinity, you have the green light to use L'Hopital's rule, discovered by John Bernoulli. All right, and then we have other indeterminate forms that show up, and a lot of forms that we might mistake for indeterminate, so I want to be sure to recognize these indeterminate forms that I have scribbled out here. Now here we have a product, 0 times infinity. Well, which one wins? Well, hasn't been determined yet. Infinity minus infinity. These are both indeterminate forms, and so are these other ones here. These are all indeterminate forms. Now, the first two that I talked about have the product, and here I have a difference, right? Product and a difference. Those are indeterminate forms that show up. Now over here I have exponents. You see the exponent. These are exponential statements here. Well, my handwriting got a little messy in here for the crowded space. These are exponential. And so what we have then is we have these three different exponential expressions that are indeterminate. So let's see, we've got 1, 2, 3, 4, 5, 6, 7. And just a quick overview when these things show up. For these two right here, we're going to use L'Hopital's rule. Now when we end up with a product 0 times infinity, what we're going to do is we're going to write it as a quotient so that we have L'Hopital's rule. And when we have a difference, we're going to write it as a quotient so we can use L'Hopital's rule. So let's just make a little note of that. Now we have kind of a general overview. Whether we have a product or a difference, our job will be to write it as a quotient. So, yeah, we can use L'Hopital's rule. All right, well, that leaves these other ones where we're dealing with these exponential statements. And when you deal with exponents, you've at this stage in your mathematics investigation, when you deal with exponents, logarithms are right there to help you. An exponential function and a logarithmic function, those are inverse functions of one another. So we know when we have one, we have the other one. So I'm going to make a little statement. When we are finding these indeterminate forms, we're going to use logarithms. Grab my pencil because I'm going to investigate what we know about logarithms. I'm going to make a little statement right away. If y equals, and I'll just use some notation, f of x, let's go g of x power. So g of x is our exponent here, and we have y is equal to f of x to the g of x. I like my conditional statements. If then, if this is true, then what's true is if I take the natural log of this side, so I'd have the natural log of y, I'd have the natural log of f of x to the g of x power. Now, because I have the property of logarithms, in fact, a logarithm is an exponent, right? It tells us what the power is. When you have a power of a power, you get to multiply those. So if we have this logarithm, which is an exponent, and we have another exponent, we can rewrite it by multiplying them. It's often described as a property, but I'm just going to show this arrow. This can come down here, and then I'll be multiplying by it. So natural log of y will equal g of x times the natural log of f of x, like that. And what we notice here is, oh, wow, we have a product. So if we're to do this, we now have a product Maybe I should make a little statement here. This is a product. And then what we can do is, well, let's just draw a little arrow over here. Take my scenic tour. We have a product, right? So we've turned one of these forms into a product. What do we do with that? Well, then we write it as a quotient, and we use LHospitals Rule. So now we have a pathway to deal with these 7 different indeterminate forms. So dealing with infinity can be very difficult for us, right? We really wrestle with some of these concepts, and our intuition sometimes guides us poorly. Sometimes it guides us well, sometimes it guides us poorly. But just a note here, these are not indeterminate forms here. The indeterminate forms I have been written up here. Now these are not indeterminate, okay? We got infinity plus infinity. Your intuition might say it's infinity, and your intuition would be correct. Negative infinity minus infinity, negative infinity. 0 to the infinity. Well, that's just 0, but of course the indeterminate form infinity to the 0, well, that's indeterminate. So be careful of that one. That one kind of messes with our minds a little bit, but 0 to the infinity is 0. So if 0 to the infinity is 0 and we encounter 0 to the negative infinity, we could write this negative exponent down here in the denominator, 1 over 0 to the infinity, but 0 to the infinity is 0. 1 divided by 0, that's infinity. Well, kind of tough one sometimes, but infinity times infinity is infinity, and if we have a negative in front of either one of those, of course we have negative infinity. So these are not indeterminate forms. So you'll run across those when you're dealing with your indeterminate forms. So now that we have our little roadmap to these different indeterminate forms, let's take a look at some examples. I am going to write down one more statement here under when we use logarithms. There's another truth of logarithms, recognizing that the exponential function base e and the natural log function, those are inverse functions of one another. So I'm going to make that statement here. We can use this route, or we can use another one. So let me just copy. So I've just put a little or connective in here. This is true. Now this one I didn't write y equals f of x to the g of x. I just wrote f of x to the g of x. This is just a little different notation. But what I'm going to do then is say I could take e to the natural log, a composite there would cancel each other out when I put something in here, such as, well, this f of x to the g of x power, like that. So this is true because these functions cancel each other out. They're inverse functions. So this is starting out with a true statement. And now I'll use, again, that property of logarithms. So f of x to the g of x power is equal to, and what I'll do is I'll just draw that arrow in there like I did before because it's the exact same thing going on. So here we have it. F to the g of x, f of x to the g of x is equal to e to the g of x times the natural log of f of x. Now let's look at a few examples. Tangent of 4z. I'm just going to put parentheses around the argument in here. So a lot of times in textbooks we won't see those parentheses. I like them. They don't cost you any money to put them in there. But as z approaches 0, we have this tangent of 0 divided by tangent of 0. So we have this 0 over 0. And I like to write it down here. This is something that I've got in the habit of. I can't use that as my answer because it's an indeterminate form, that quotient form of the indeterminate form as 0 over 0. But it does give us a green light then to take the derivative of the numerator, then also take the derivative of the denominator, and that's LHospitals rule. So you could use an H here for L'Hopital, or an L for L'Hopital, or you could use a B for Bernoulli if you wanted to. And now, incidentally, L'Hospitals Rule, it's spelled a couple different ways. So if you're looking for other tutorials on L'Hospitals Rule, you of course recognized how I had written it. I'm going to give you another spelling of L'Hospitals Rule. This is another spelling of L'Hospitals Rule. There we go. So I took the derivative. Of course, the derivative of a tangent of this is a tangent, and it's a composite tangent of that 4z. So it would be tangent of some garbage, right? So that's secant squared of the garbage times the derivative of the garbage. I don't know if you've seen another one of my videos where I use the language garbage for those quotients, but at any rate, we have to write down our limit as z goes to 0, and I'm going to write the derivative of that garbage is 4, right, with respect to z. So I'm going to write 4 secant squared 4z. And again, I'll put those parentheses around there. And here we have tangent of the garbage is, the derivative of tangent of this garbage is secant squared of the garbage times the derivative of the garbage. Like so. Now, as z goes to 0, secant of 4z, when z goes to 0, I have secant of 0. Secant of 0. Now, if you're not sure what secant of 0 is, we do have our calculators that we can use. Of course, we should know this at this point, but I'm going to find a calculator here and see what mode it's in. This one's got a little bit of battery power left. I pushed mode. It is in radian mode, so I'm going to use my calculator to help me remember what this secant of 0 is. And once I find that value, I'll square it. Using my calculator for secant of 0, of course, secant is the reciprocal of cosine, so secant of 0 is 1 divided by cosine of 0, which I typed in here, to just illustrate that it is equal to 1, although, yeah, you probably knew that, and I just wasted a bunch of your time. So if this is all equal to 1, and this is all equal to 1, we have all of this then is equal to 4/7. Say we're moving on. I'm just going to kind of celebrate my answer there a little bit. I've got another example problem, and when we find these new rules, we're eager to use them right away, but be careful and always investigate first. This example is just set up more as a warning for you than anything difficult, but sine of 0, of course, is 0, so I have a 1. And we have cosine of 0, which is a 1. Now, just like before where I make a note of that indeterminate form, I'm just going to put a little box in green around that. Gives me the green light to use L'Hospitals Rule. If I don't have the indeterminate form 0 over 0 or infinity over infinity, I'm not using L'Hospitals Rule. I'm not using L'Hospitals Rule here. I don't need to. This is all equal to 1. So just watch that. Doing this right here is very helpful, just right below. I don't usually put it behind it because often when I'm investigating these, I get these indeterminate forms. So I don't want to say the answer is 0 over 0, as it was 4/7 in this case. So our next example, e to the 2x minus e to the negative 2x minus 4x all over the quantity x minus sine of x. Now x is approaching 0 from both directions. And I notice I have e to the 0, which is 1, minus e to the 0, which is 1. So we've got 1 minus 1, that's all gone. Minus 4 times 0, which is 0. So I have a 0 in the numerator. 0, sine of 0 is 0. So I got a 0 in the denominator. A green light to use L'Hospitals Rule. So I'm going to go ahead and do that. And then, of course, I'm going to record my limit statement. And I'm going to take the derivatives. Sometimes I need to go use some scratch work to take derivatives. This one looks like it's pretty easy. So we'll have 2e to the 2x minus a negative 2. So record that as plus 2e to the negative 2x minus 4, like so. 1 minus cosine of x, like this. Now I'll substitute in my zeros again to see as x approaches 0. So I get x approaching 0, e to the 0. Same kind of the same thing. 2 plus 2 minus 4. We got a 0 in the numerator. And 1 minus cosine of 0. Cosine of 0 is 1, so we get 0. We get this indeterminate form again. So we'll just keep using LHospitals Rule. Take the derivative again. 4e to the 2x minus 4e to the negative 2x. I'm just going to check the sign here real quick. Yep, that's looking okay. And our denominator is the derivative of negative cosine. Of course, the derivative of cosine is negative sine, so the negative derivative of cosine is sine of x. There we go. And we're letting x go to 0, not infinity. I don't know why I wrote an infinity symbol here. Let me just try to correct that with a big, ugly 0. I don't want to change where x is going midstream here. That would be pretty wild, right? So now what we have is 0 over 0 again. Will it ever end? Well, it looks like we're going to have a denominator that is non-zero here. The denominator is 1 because cosine of 0 is 1. The numerator looks like we've got 8 and 8 added together, so we've got a 16. So it looks like no use of LHospitals Rule here at the end. Just a reminder, hopefully you like this technique of writing it below. It'll tell you what you're permitted to do. It'll also tell you when you're done. I'm not going to put a green box around this one because it's not that indeterminate form. But we will celebrate our answer. Looks like it's equal to 16. Now, I'm also going to do one more thing here. I'm going to take a look at what's going on with this function right here. What's going on with this function right here? Now, we might not know what that looks like graphically by examining this. I don't. But my calculator will help me by plotting points and so forth. So I'm going to reach for my calculator, and I'm going to put this into y1 in my calculator just to check this out. I'm just going to use a little graphing calculator help to see if this 16 sounds reasonable. Grabbed my calculator and I carefully typed in the numerator enclosed in parentheses and the denominator also enclosed in parentheses. Make sure you do that because otherwise your calculator will do exactly what you told it to. And we want to make sure that we tell it the right thing. So my suspicion is this is equal to 16 if I've done the math right. Maybe the easiest way there is to go to our table and substitute in 0. Now when I hit enter, you're calling me out on this. You're saying, hey, wait a second, it's not going to assign anything to it because when you put in the 0, you get a 0 over 0. So yeah, you're right. I could numerically approximate this with something close to 0. Here I'm doing it from the right. I could do something close to 0 from the left. And it looks like it's probably going to be around that 16. Right, I could get a little bit closer. I'm just going to make sure my radian mode is on as I'm doing this. 0.0001. Let's see if we... Oh. Oh, bother. Well, this numerical approach gave a little bit of support that we think it's probably around 16, but then when I got a lot closer, my calculator's saying it's dumping to 0. I don't know why I typed that one in there twice, but I did. So maybe a graphical approach will help us. The numerical approach can help us, but it might be difficult to see. So I'm going to hit zoom standard. And as soon as I did that, I realized, well, if I'm thinking this thing's equal to 16 as x approaches 0, I'm going to have to stretch this y-axis out a little bit bigger. So I want to see what this looks like graphically. So now I have a max of 10. I'm just going to hit the window. I'm going to go y max. Let's go way beyond 16. Let's go to 50. You don't have to change the scale, but it just looks a little bit, I think it looks a little bit nicer. I'm going to hit graph, and then we have our scale of 10. So if it is 16, it should be coming in right about there. Now, I think this helps us see it a little bit better that the limit as x approaches 0 from both directions is 16. It is, but now we have a little bit of graphical support. So use your calculator when you're not fully convinced or you just want to double check yourself. Next example, I've got e to the 2x divided by x minus 1 over x. And we're looking for the limit as x approaches 0 from both directions. What I'm going to see right away is when I have e to the 2x and x is approaching 0, I have e to the 0. It's going to be 1. 1 and then x approach 1 over 0. Now 1 over 0 does go to infinity. So I'm just going to, I make myself some notes so I don't have to do it all in my head. This is infinity. Now as x goes to 0, I have that 1 over 0 again, and that's infinity. So I have infinity minus infinity. That's the indeterminate form, that difference form of the indeterminate form. Now I grabbed my red pen there. I don't have the green light to do LHospitals Rule. But remember our little flow chart here, write that as a quotient, then yeah, you can use LHospitals Rule. So let's give that one a go. I'm going to write it as a quotient. And let's see what this looks like now. 1 minus 1 is 0 over 0. There's our green light to use LHospitals Rule. So I'll make that note. I typically just got in the habit of using an H when I'm using LHospitals Rule. Use an L or a B, whatever you would care to use. Just don't dump your limit statement and watch where you're letting x tend to. Sometimes we can write the wrong thing down. So derivative of e to the 2x is 2. E to the 2x, derivative of negative 1 is 0. Derivative of x with respect to x is 1. So it looks like this. There's the use of LHospitals Rule. This one gets pretty easy to finish up, and I can finish it up right in this space right here. Celebrate a little bit. Throw that into your calculator if you want to check. You should be able to determine or support your answer of 2. Check out this example. I have the quantity 1 plus 1 over x, all raised to this exponent x. Now what's happening is x is growing without bound, so we write it this way. Now let's try to wrap our head around this one piece by piece. I'll start on the inside here. As x goes to infinity, I have 1 divided by infinity. I like to use the analogy, a loaf of bread. 1 loaf of bread divided by infinitely many people. Everybody gets 0 bread, right? So now in the parentheses, I have 1 plus 0. So I got a 1. And as x goes to infinity, I'll just show it this way. It goes to infinity. I have this 1 plus 0 to the infinity. So it's not 0 to the infinity, but rather 1 to the infinity. Which I'm just going to write down here. that's indeterminate form. We're going to use a logarithm to see if we can determine what this, if anything, is equal to. If it's equal to something, then we say this converges. If it's not equal to a value, then we say it diverges. We just don't know yet, but we're going to investigate. So I'm going to grab my different colored pen just to let it stand out a little bit. And I'm going to use this technique right here. I think this will be a fine technique to use. I'm going to say y is equal to that thing that we just don't know. I'll find myself a new red pen. This one's what I'll do then is I'm going to take the natural log of both sides. Now this will be a little bit tedious, so I'm going to have a large piece of paper so I can work my way through this. And it looks like this. Now just a note, if this is bothering you a little bit right here, where I have the natural log of this limit, let me just put some big square brackets around here to kind of be dramatic and draw a little attention to it. We've dealt with limits and logarithms before, so just a little note. If we have the limit of the natural log of a function as x approaches a, it's the same thing as the natural log of the limit as x approaches a of f of x. With a caveat here, I should add the little caveat. If you're going to put this note in your notes, here's the caveat. As x approaches a, the limit of that function must be greater than 0. So let's just kind of inspect that to see if that holds up. So this is a caveat to this limit rule or limit law. I don't usually call them laws or rules. They're just truths, things that are true. But will this always be positive? As x grows without bound, we have these values getting larger. So yes, that's going to be greater than 0. So this is totally true. I can now write this just a little bit differently, which will be helpful for me. I can actually write the limit statement out here and then the natural log here. It's just looking like this, and of course the reason we wanted to do this is so that we could use that property of logarithms to write it as a product. And after we write it as a product, we still have some more work to do potentially, so let's see where this takes us. I'll grab my pencil as x goes to infinity. Now I have 1 over infinity, loaf of bread, 1 loaf of bread over infinitely many people. They get 0 bread, right? The natural log of 1 plus 0 is 0, so all of this, I might say, all of this here then goes to the natural log of 1. That all goes to 0, so I have infinity. Let me just grab my red pen. I've got infinity times 0. There we go. So I had 1 to the infinity. Now I have infinity times 0, which is still indeterminate. Started with 1 to the infinity power, and we used logarithms so that we could write it as a product. That's what we have now. And when we had that product, we had to do something with that so we could get over here to the green light for LHospitals Rule. So as we look at it, we're going to have to be a little bit clever and see if we can come up with a way of rewriting that as a quotient. So I want to rewrite this as a quotient. Actually, I want to rewrite this as a quotient, so I have that green light. So I wrote down a little bit for us here. Pause the video and I wrote this down. I have the natural log of this stuff right here, and it's times x, which is the same thing as multiplying by the, or dividing by the reciprocal. 1 over x. There we go. So this would do it. In fact, if this is what we're looking at, I now have loaf of bread divided by infinity to get 0. Bread, 0, natural log of 1 is 0. I have the 0 over 0 indeterminate form, so I can use LHospitals Rule. Now I'm going to have to take some derivatives. I need the derivative of the top, and I need the derivative of the bottom. These are both going to be very, very easy for me to do. So let's go ahead and do that. I'm going to pause the video, and then I'm going to do that work, and I'm going to write out the derivative of the natural log of 1 plus 1 over x. It's the derivative of what's inside divided by what's inside. And this denominator here is x to the negative 1, so the derivative of x to the negative 1 will be negative x to the negative 2. This is going to be pretty easy. All right, you can see if you have an equivalent derivative now in the numerator and the denominator. So it looks like this. I didn't finish this one up. Of course, the derivative of 1 over x is negative x to the negative 2. I put it over 1 so that I could take this fraction and multiply it by the reciprocal of this fraction. I'm going to see those negative x to the negative 2's cancel out. So what I'm going to put here is just an equals the limit as x approaches infinity of, what do we have here? Because if the negative x to the negative 2's cancel out, I just have 1 over 1 plus 1 over x, like this. All right, well, let me grab my pencil, see what's happening here. A loaf of bread divided by infinitely many people. You're probably getting tired of that one. I got to quit using it. This is all equal to 1. So I'm going to celebrate my answer. Oh, I'm off the screen there. Celebrate the answer, maybe, but you know what I have is the natural log of y is equal to 1. So I think what I'll do is I'll just bring these two statements here as together. Natural log of y is equal to 1. But remember, what I really want is I want y, because y was what I was looking for. This is what I want to say. Well, what are you equal to, y? And so, I'll use my knowledge of exponential functions, and notice that if I take e and use those both sides of the equation as the exponents, I have y is equal to e to the 1, which is pretty exciting because we found that that statement, the limit as x approaches infinity of the quantity 1 plus 1 over x to the x, is actually equal to e. And that's pretty exciting. I want to put an exclamation mark, but it would look like a factorial. We'll not do that. Thanks for watching. I hope this has helped a bit.